We'll start. Welcome everybody to today's lunchtime lecture. And before I hand over to Sifiso, just some housekeeping rules. Everybody, please make sure that your mic is muted and that your video is off. It saves bandwidth for everybody. There is the chat button at the bottom. You may ask questions through that, or you may simply raise your hand during question time and we'll ask you. If the system crashes, simply just log in again and all will be fine. And before I hand over to Sifiso, just a quick thanks to CoreStore for being the June sponsors of these lunchtime lectures. So Sifiso, if you'd like to introduce Herman.
Great, thanks Tanya, thank you very much. And that is GeoExplore Store, our sponsor, so thank you to them and thank you guys for attending as well. Just a bio about Dr. Herman Dorland. He holds a PhD in geology from University of Johannesburg. During his thesis, he worked on regional correlations of sedimentary successions on the Kaapvaal craton using paleomagnetic analysis and zircon geochronology. Following the completion of his PhD in 2004, he spent a year working as a postdoctorate researcher at University of Ottawa, that's in Canada. In 2006, he then joined Anglo Coal, where he worked first logging core and later as a geological modeler. He was a senior geologist there. Then in 2012, he joined Snowden Consulting as a senior consultant, working mostly on reviews for banks on coal projects. From 2015 to 2018, he worked as a research associate at the University of Johannesburg. After that, he started his own company, Virtual Geomet, which develops software for geometallurgy and undertakes projects as well. Today, Dr. Herman Dorland will talk to us about the characteristics of washability and liberation. Thank you. Please go ahead, Herman.
Thank you, Sifiso, for the introduction. Yeah, I worked in the coal industry for a couple of years, and when people think of washability and liberation, they really think of washability analysis. And this analysis, they take an exploration sample from drilled core, they crush it to a certain particle, a top size in a crusher, usually minus 25 millimeters in Witbank. They then take the crushed material and put it through different density fluids and analyze the floats and the sinks for quality. But I was always interested in washability, and I was, from the beginning, started to think, is that all there is to washability? So let's see. So here's the outline of my talk. I'm going to talk about 3 points today: the breakage of particles, washability, liberation, simulation, and some conclusions. To start with, yeah, if you think of breaking a particle, in how many ways can you break a particle in two? So here is a particle, just a simple particle, and here is the first crack at exactly in half of the particle, breaking the particle into two exactly the same pieces. So, but then now if we say that we know washability, then we are able and know all the ways that the particle can break. Then we can go and list all the possible breakage patterns in a table. So from breakage pattern 1 to breakage pattern X. And then we can say that now we have all the breakage patterns that's possible. However, then we can go and the breakage pattern, we can go and change this 5, the decimal 5 to a 6, the 1 to a 2, this 1 to a 2, the 0 to a 1, and so forth for all the possible breakage patterns that we listed. So then we obtained a number that is different from all the numbers that we listed in our table that we thought was a complete list of all the breakage patterns. So we get a unique number different in all the numbers. So in fact, there's a contradiction. We did not have all the breakage patterns listed. We can always in this way obtain at least one extra pattern. So this is a way in which to prove infinity. So there's uncountably infinite many breakage patterns to break a particle in two. Unlike people think it's just a few patterns, there's infinitely many. And in the same way, you can look at a more complex breakage pattern, say you want to break the particle in 6 pieces, then you can find the 6 new unique breakage patterns in the same way by this diagonalization argument, and so forth, and carry on and find 6 more and 6 more. So we have also infinitely many complex breakage patterns that we can find in this way. So just to summarize what I said, there's infinitely many breakage patterns for breaking a particle in 2. By the same diagonalization process, it can be shown that there exists infinitely many breakage patterns to break a particle in more than 2 pieces. And therefore, the probability of predicting what breakage the pattern will form, the naive probability is 1 over infinity, so that it's 0. So it's impossible to predict what breakage pattern will form. And this has implications for washability, understanding washability. Now I want to talk a little bit about simulation of washability. It's a method to describe washability in more detail than a single float sink test that Virtual Geomet developed over the past 3 years. So this is a eulite ironstone. It's an iron ore from here in South America. It's a scan with a normal office scanner. This is a 1 millimeter scale barrier in the bottom right corner. So these oolites are about 500 micron in size. And if we look at growth rings, then we can see down to about 5 micron or 2 micron per pixel. And there's different minerals in the eulite ironstone. There's the hematite. The hematite is red and the gray. There's the there's other minerals as well. There's yellow mineral and the quartz as well. So what we then do is we take this image, we indicate in certain spots the graphite, the hematite, the quartz, and then we train the software with the spots, and the software going by artificial intelligence methods go and map out the rest of the image based on the training. And then obtain a quantified map of the minerals of the image that we mapped. We then apply certain assumptions to the minerals. For example, hematite has got a density of 5.3 grams per cubic centimeter and an Fe2O3 weight percent content of 100. This is well known. It's a strong assumption. For graphite limonite, the assumption is not as strong because there's some variable water and Fe2O3 contents in this mineral, but we make an assumption for it and a density of 3.8. So we assign these values to the minerals in the map. The output from this, using the quantified map in these assumptions, we can then output the volume percent of the minerals. For example, the hematite 45%, the hematite 1 45%, and the quartz 14.8%. We can then estimate the oxide, the weight percent oxide, major oxides from there, Fe2O3, for example, or FeO for the minerals we know that we made the assumptions for. And from there we can calculate, knowing the length of a sample and the radius of the core, we can calculate density based on the volume percent of the minerals, and we can also then calculate the mass using the volume and the density. We can calculate mass, and this mass can later be used to composite different samples using the simulation method. There's other inputs that we make is in the simulations, the particle size distribution. We assign a certain particle size distribution to the virtual particles that we want the software to break the sample into. And for example, this is a 0.1 millimeter particle, 0.2, and different percentages. The software then takes this input and break it as close as possible to what the input was. This is just what the same image, and on it is indicated the 2 millimeter particles. You can see that there's not much liberation going on here. All the particles are more or less the average of the entire sample, the mineralogy. And you can see the coarse and the hematite and the goethite and the grey hematite. So there's not much liberation. So at 2 millimeter particle size, you won't get much product or liberation of quartz to obtain a better product. This is 1 millimeter simulated breakage pattern. Again, the same problem, it's still not liberating. There's still lots of quartz mixed with the hematite in here. However, at 1 millimeter, at 0.1 millimeter, you get very good liberation of the goethite and the hematite, all minerals, and we separate the quartz from all minerals, and yeah, we get a much higher yield than, for example, for a 5% SiO2 product at 0.1 millimeter and at 2 millimeters. And yeah, the software then uses these virtual particles and calculate or estimate the washability. These washabilities are these are averaged for 5 simulations, each at the different sizes for 2 millimeters, 1 millimeter, 0.5, and 0.1 millimeter. If you want to look at the 5% SiO2, this is SiO2. We're looking at 5% SiO2. This is about 30% yield for 5% SiO2 product, and the 2 millimeter particles is about the 40% yield of 5% SiO2 product and 1 millimeter particles. But then for 0.5 millimeters, there's about a 92% yield for 5% SiO2 product, and the same, more or less the same for the 0.1 millimeter size fraction. So we can see we're optimizing the yield and liberation around 0.5 millimeter, where we have the maximum yield for the biggest particles. And this type of analysis is not possible with traditional physical floating tests, where you can only crush a sample once and analyze it once at a certain PSD of which you only know the top size. This is just all the washabilities I've just shown you plotted on one graph. For the average 2 millimeter yield, you can see it's very steep. So there's lots of near-density material and there's not much liberation. All the particles are more or less the same quality. And this is when you list the 0.5 millimeter and 0.1 millimeter yield is this one. If one look for this is the ash for the 0.1, 0.5. They plot exactly on top of each other. If you look at a 5% ash, see there's a 92% yield, and you see that the curve is flat in this region. So there's very little near density material, and this makes predictability of what will happen in the plant easier than this very steep curve where small changes in the density creates large differences in the SiO2 content. So what happens if we simulate the 0.5 millimeters particle several times? So we make different particles each time for 5 simulations. We break the quantitative map 5 times into different simulation breakage patterns. If you look at this, then the 5% SiO2 product is around 3.7 grams per cubic centimeter, and it's got about a yield of 93 all through. So these curves, if one plot them, they plot almost exactly on top of each other, the yield curves and the ash curves. So for the 5% SiO2 product, you get about a 92% yield. And again, we see that the curve is quite flat in the region of the 5% SiO2 product. However, if we go to the 2 millimeter particles again, for the 5% SiO2 product, we see it's sitting at a density of about 4.7 grams per cubic centimeter. And in this case, it's got about a 25% yield, 30% yield. In this case, it doesn't make the product quality cutoff. So you have 0 yield, and here in the last 3 simulations, there was 0 yield for the 5% SiO2 product. So, and this is just to demonstrate these curves are variable. You can form very different washabilities for the same PSD from the same sample at 2 millimeter particle size in the Geological Einstein. This is just a summary diagram of what I just said. This is the particle size in millimeter, 0.1, 0.5, 1 and 2 millimeters. Looking at the 5% SiO2 yield, we can see for the 2 millimeters, the yield varies between, for the same sample, it can vary between 0 and about 55% yield for a 5% SiO2 product. The yield doesn't improve, but the predictability improves. At 1 millimeter, the yield varies between 45 and 55%. But then we see at 0.5 millimeters, there's a great increase in 5% SiO2 yield, and the predictability is high because the yield varies between 91 and 93%. And there's not much difference in yield or predictability going to 0.1. So in this case, we can see that the 0.5 millimeters particle size probably gives the best solution for these Geological Einstein ores. So just my first conclusion slide, which is more practical. For sample preparation in most rocks, you just need a cut surface made by diamond saw, which is then scanned by office scanner, that you can go down in with a modern office scanner, you can go down to a resolution of about 2 micron per pixel. From the quantitative maps, you can then estimate the mineral composition and the major element chemistry quickly. You can do it almost within an hour or half an hour of cutting the sample. You can have that information for your Einstein ore. And then the washability can be simulated and estimated for many different particle size distributions, and it can be quickly done, unlike the traditional float sink test that you can only do 1 crush per sample and estimate 1 washability. So from this work, you can quickly find a good estimate for the best particle size to break to for a certain ore. Just to show that it's not only for Geological Einstein, this is a laminated iron ore. Here is the particles, the positions where I train the software. It then goes and maps the software. It uses 2 methods to quantitatively map, which is then for the final classification. It takes these 2 methods and it gets a weighted average. This is an igneous rock veins. You can see this is 6 centimeter scale. So, for example, this is different in QuemScan. Because you can analyze a big sample quite rapidly, and again, it gives you quite a good representation of the mineralogy in the sample. This is a sample of a porphyry. I scanned it at 2,400 dots per inch, and at this resolution, you can see in individual crystals at high resolution, and you get a very good indication of the amount of metals in the sample. For coal, it's a bit different. You need a polished surface because with a normal cut surface, you cannot see the contacts, the boundaries between the macerials and the minerals, so it's difficult to map. But here I indicate from a polished sample, polished surface, what you can do. This is different resolutions that I map at, and this is 300 dots per inch, 600 dots per inch, and 1,200 dots per inch. At 1,200 dots per inch, you can see a lot of detail, and you see much less detail at 300 dots per inch. But for coal, probably 600 dots per inch is a good resolution to map at for this type of simulation work. This is another example of why one can use this method to estimate the grade of a sample. If I crush a sample and I take a subsample from the analysis, then I can overestimate or underestimate the grade of the sample. For example, if I sample like this, if I sample the gangue, the gangue minerals, the gangue material, and the spotted orange dots is the ore material. So if I sample like this, I oversample the ore minerals and I undersample the gangue, then I get the overrepresentation of the grade. So where I know the average grade is 20 grams per ton, with overrepresentation of the ore, I will get 30 grams per ton, for example, in this, by taking a subsample. And I can also oversample the gangue minerals and undersample the ore minerals, the ore material, and then I get a grade of 8 grams per ton from the same sample, just taking different subsamples. But with the method of analyzing an image, you get a proportional representative sample as indicated by this green line, which is possibly impossible to obtain using subsampling from a crushed material or a milled material. So just some importance to the mining industry. We have seen there is variability in prediction between particle sizes. A 2 millimeter crush size is not the same as a 0.5 millimeter crush size for the electric iron sand. You develop very different washabilities and predictability. For example, for measured resource, that you need to be within 10% error, your resource estimation. This is not possible for a 2 millimeter particle because the weight percent yield varies for the 5% SiO2 product between 0 and about 55%. So that the variability is great. So you can never come within the 10% error of estimation. But we've seen for the 0.5 millimeter particles, the washability behaves highly predictable, and the yield varies between 91 and 93. So this at this size, you can get a measured resource. So it's important that resource reserves are reported at specific particle size. And the reconciliation between resource and plant depends on particle size. In the 2 millimeter particles, the washability behaves very unpredictable. So you don't know what you're going to get in the plant. You don't know what washability you're going to get. But at 0.5, the washability is predictable. It's easier to perform reconciliation work between plant and resource. And yeah, particle size versus location analysis is important for plant design. This is not possible with traditional floating tests. I can do hundreds of simulations at different particle sizes with simulation, but I can only do one floating test per crush. There's some other estimations of resources that was in the news. For example, this is a project that was reported in July 2011. They thought that this coal deposit in Mozambique is similar to the Bone Basin in Australia. The company went and bought a product for about $4 billion in 2011. In January 2013, they wrote off $3 billion of this project. The two main reasons given was that the infrastructure had proved more challenging than expected, and estimates of recoverable coking coal used in steel productions were lower than expected. So this company did float sink in the traditional float sink test, but they still, when they operated the plant, they got much less than they expected from the coal. And then in July 2014, they reported that the project was sold for $50 million. The $4 billion project was sold for $50 million to another company. Here is an example from the news for a problem with plant design. This is a project in the Limpopo coalfield in South Africa. The company went and built a plant. It never produced what it was supposed to, semi-soft coking coal. I come to a conclusion that the plant is not working. To put it bluntly, it appears to be a dud. So they did float sink test, the traditional float sink test, but again, when they operated the plant, they got something completely else than they expected. This is just a discussion, it's more theoretical. So the prediction of washability and liberation improves the small particle sizes. At small sizes for rhyolitic ironstone, washability is highly predictable. And then washability behaves in a conditional probabilistic fashion. The particle size influence the probability of certain washabilities forming. We've seen for 2 millimeter particles in the rhyolitic ironstone, the washability is highly unpredictable, but at 0.5 is very predictable. At small sizes where components are better liberated, breakage pattern plays a significant role. So a significantly smaller role than predicting washability at larger particles. This is just so for small particles, you make the same washability. It doesn't matter the breakage pattern, but for large particles, it may depend on certain contacts between minerals. It may break there, and you may know, and you may notice. So we are in the process of developing a software for that follows breakage rules. So you can tell the software, when you see this boundary, you stop the growth of the particle at that boundary. So you don't go over this boundary, and you can do it with isolation in mathematics. Just another the same slide to show this conditional probability at the 2 millimeter particle size is highly unpredictable. But if you know you're in 0.5, the washability behaves predictable. There's just some theories and principles that I've applied to the work I'm currently doing. I will read this because it's quite complex to say it concisely in my own words. So the breakage patterns and the related washabilities cannot be fully described. In order to disprove this theorem, it needs to be shown that it's possible to have the complete set of possible breakage patterns. That is the amount of breakage patterns of a finite piece of material is not infinite. But we've shown that in the first few slides that breakage patterns is uncountably infinite. So I don't know how you're going to disprove that. So the second principle is that it's not possible to measure exactly washability formed. In order to disprove this principle, it is necessary to be able to show that the exact shape and density of each particle is known, and a stricter definition of this would be the requirement that the exact breakage pattern out of which the particles form should also be known. So you must know everything about the washability to be able to exactly measure it. Then a third principle is that we cannot predict the exact washability curve that will form in a plant or laboratory for a given crush of a sample washation, and then find the exact washability in the laboratory or in the plant. And then, apart from some error introduced due to the two-dimensional quantitative maps used to approximate the three-dimensional volume, all the single washabilities are true for the sample simulated. So these simulations are not figments of our imagination. They are logical conclusions using the mathematics that we apply. So, however, these true these simulations can never be obtained by physical tests. This is related to a result in logic obtained by Goodell in 1931, that not all true mathematical statements can be proved within a system in which they exist. So, although these washability simulations are logical truths, they can never be proved completely or verified by physical tests. And then also probability in washability is conditional. So therefore Bayesian probability methods can be applied. As we've seen in the previous figure, there's different probabilities of washability forming at different particle sizes. So the particle size is the condition on which to base the washability that you predict. So final conclusions. Washability is an infinite mathematical object that you cannot fully describe and for which predicting the exact washability. The naive probability is 1 over infinity, so it tends to 0, that you will ever predict the exact washability that will form. I think for this type of result, we spoke last week about sending samples to many different labs to see if they can reproduce the answers you get. But in this case, it won't happen. And I think in many cases, you won't find reproducibility for many types of analysis in the geosciences. Simulation demonstrated washability behaves in a conditional probabilistic fashion. So you can simulate for many different particle sizes and see how the predictability changes. Although simulations represent logical truths, they cannot be physically completely verified. The economic evaluation of resources, mine and plant design to consider improved understanding of washability for different particle sizes. And this type of evaluation is only possible by simulation and not with physical liberation tests. And the washability that is produced in the plant should be a consensus decision based on economic value processing practicalities, not left to a chance outcome. With that, I say thank you for listening, and here is my contact information. And here is a classification of solid by Vincent van Gogh using our software. Maybe a last statement is washability. Yeah, I don't think we should think of washability as just a physical test. Using the crushed material at different put through different density liquids. I think it's an infinite mathematical object that is much more interesting than is currently thought in the industry. Thank you for listening.
Thank you, Herman. A very interesting discussion on washabilities. I'll open the floor now. If there are any questions, just please raise your hand.
Sorry.
Yeah, go ahead, Saleh.
Just what, Herman, thanks very much. Very, very nice talk. We're helping you with some of the aspects of this research. Just from our experience, and again, I'm not a coal expert, but from my time spending at, can you hear me?
Yes.
Yes.
Yeah. From my time spending at Exaro Research, where we did a lot of coal work and coal research work, the one thing that we realized, and I think many mining companies, the examples that you've also given from the Mozambican example, many companies doesn't realize this, is that when you do the geology and you do it from drill core, you look at only one aspect of your coal ore body. And when you then go into operation, you then bring in a lot of other factors. And a simple factor, let me just identify one simple factor, and that is, for instance, your blast pattern. So depending on the blast pattern that the mining engineers choose, your coal will break a certain way. And if that blast pattern is not tested up front, and you actually determine your washabilities and how your coal will handle through your plant based on how it will actually break during mining, you are in deep trouble. So that's the one aspect. The other aspect is getting representative samples of coal. And the biggest mistake that companies also make is they take very small samples. They, for instance, will take, using an example again, they will take a large diameter drill core and over, say, 300, 400 meters intervals, and then they will use that single intersection of a large diameter drill core to postulate what will now happen 300 meters in the, on either side of that drill hole. And we know from the data that is available from, in this example, from the Exaro ore bodies, that that's not possible. So, and that relates all back to, first of all, you're not taking into account what will happen during mining. Second of all, your sample size is way too small. And the only way you can actually then postulate accurately what will happen when your coal eventually hit that plant is actually to simulate precisely what will happen. So you have to know how your coal will break during blasting, and you also have to increase your sample sizes. Sorry, I'm finished.
Okay,
thank you, Solly. Yeah, I agree with you. We're working on the breakage rules to see if we can simulate what the breakage is that we see with the simulation. For bigger samples, I think you need to really analyze how far the coal remains the same over distance. So in the mine phase, you need to go and take these images of blocks over 10 meters or 5 meters and see how far the coal remains the same, or more or less the same, and how far the washabilities will behave the same. So, but that's another type of study. So but I agree with you. We don't understand the coal. We build a plant and it doesn't work as we expected.
Yeah, just a comment on that. Companies have wasted billions of rands, as you have mentioned, and that is not the only company. That's not the only company that you've given an example of. There's many operating companies in South Africa who have wasted billions of rands because they don't want to take a big enough sample and then wash that sample. See, I'm still a believer, a great believer. Sorry about that. I'm still a great believer in physical washability tests. I just think it's done incorrectly. People want to save money on it. And if you do a washability test, if you really want to do very, very accurate washability tests, you actually have to take a very, very big sample, crush it to a number of sizes, and wash at each of those sizes. And then on top of that, you must be able to, as I said, you must be able to simulate also what will happen during mining. And this is now already a couple of years back. We estimated that it will, for any washability test that you do, it will cost you about R1 million. So if you do one big sample, wash it the right way, crush it at different sizes and wash it correctly, physical washing test, it will doing the associated with it will cost you R1 million, and very few companies wants to spend that R1 million, but they're actually willing to lose billions later on. They're willing to lose billions later on, but not willing to spend a couple of R1 million in characterizing their coals.
I don't think that is limited to coal deposits, Solly.
Yeah.
Michelle van Staden, you have a question that you'd like to ask?
Yes, hi. Michael van Staden here. Yes, not Michelle. No problem. Thank you very much for that presentation, Herman. It's certainly a topic which, being a geometallurgist myself, but very much focused on the diamond industry. Maybe first of all, a question to you, and then a few comments which you might want to respond to. But have you ever tried something similar on a kimberlite ore type? Or have you played around with kimberlites, with all the various heavy minerals that are stuck inside kimberlites?
I've not worked on kimberlites, but I think you can. If you look at the different crush sizes, how breakage will, if you can simulate the breakage rules of how kimberlite behaves during blasting and crushing, you can probably simulate what type of sizes you can get at a certain crush size, what size of diamonds will still be preserved, and what is the probability that you will preserve a diamond at that size. So you can simulate that kind of information, and going to smaller crush sizes, what diamonds you can extract at smaller sizes, and what is the likelihood that you will that the sample, that the diamonds will be preserved.
Yeah, that's very important, and there is actually within the larger companies such as De Beers and so forth, that type of research has obviously always been happening. It would be nice to have a chat at some stage to just align some thoughts. But you did right. There's a cutoff point where in diamond industry you cannot crush too fine. Obviously, you're going to start breaking diamonds. So that's a very, very important sort of let's call it a crushability size that you should be targeting and not exceeding that. But what is important for us is, from a geomet viewpoint, is to understand how the plant one day will handle materials that are going to be coming to the plant from a geological model point of view. And as has been mentioned, it's very expensive to do these various, to do washability curves. It is an expensive exercise. And, you know, I believe, as Solly also said earlier on, I also believe in the washability, the actual practical execution of these washability tests. But I would also like to say that the resolution from a geomet model point of view is going to be not that high, because it's a very, very expensive and a very, you know, you're going to need many, many samples as well. So I would like to suggest maybe at some stage we can maybe have a chat around this, because this could be supplementary in a big way. Or maybe not. Maybe the washability tests could be supplementary to this type of work, rather, let's put it that way around. Where this almost becomes your proxy test, so to speak, and the washabilities are just there to validate things a little bit. I don't know if you have a comment on something like that.
Yeah, yeah, the simulation must guide you. So if you see you want your diamonds, you see the size that you want them, that you think your diamonds are at, that you want to preserve and not crush and also extract, then you can simulate for that. And if you then take a bulk sample and do an analysis at what the simulation suggested for you, and you get more or less the same thing, then you know that you can, yeah, then it's a valuable then it becomes a method to simulate any kimberlites quite inexpensively, because it doesn't take much money to cut the core and scan it and do the simulations using a computer. It's much less less expensive than doing a physical float sink test.
That's right. That's right.
So
and then the other, that sounds very interesting and aligns with my thoughts. The other last question would just be then, in terms of when you do these tests, do you do various slices? I mean, you said you use a normal optical scanner, which is, you will probably find that as you take different slices, the mineralogy inside changes. So I suppose you need to do various slices just to get a, let's call it, a representative optical measure of the various minerals, not just in one plane.
Yeah, we're only seeing one plane. With coal, we actually did a 3D tomography scan of a piece of coal, and then do slices at various depths, and then you can see, and then do washability simulation on those slices. And we, for some coals, the variability between these slices is very low, but for others it's higher, because there's a difference in the slices. But this is what I told Solly. How similar are your kimberlite or your coal over distance? So you need to do, in a mine phase, go and sample these slices and see how it changes over a meter, over 10 meters. And then you simulate for these different distances and see how it changes. If we change a lot over the meter, well, what does the boron mean anymore? Then it doesn't really mean anything. It's but if it stays the same over 10 meters or 20 meters, then the boron information, the drill core information really means a lot. So it depends on the deposit.
Yeah, I'm with you. Yeah. Okay, thank you very much. I'm going to, I'll be in contact with you outside of the meeting. I'll try and get, if you can just maybe give me your details. I didn't write it down now. Or maybe just flash that screen again, then I can write it down. Thank you very much.
Okay, the next question is Alan Golding, you've got a question? Just
Yeah,
unmute
thanks
your...
very much. Can you hear me now?
Yes, we can hear
Yes.
you.
Okay. Thanks very much. A very stimulating talk. Something a lot more mundane. Do you think you could use the same technique to determine how to liberate silica from calcrete deposits?
Yes, it's actually for all rocks. If the silicate is big enough, if it's more than about 2 microns, you can pick it up with an office scanner. Then you can map the material, the slice image, and you can simulate to see at what sizes you need to crush or to mill to liberate the silica from the calcrete. You can do that.
Oh, that sounds very interesting. I think, like Michael, I'll be in contact with you.
Okay, thanks.
Okay, thank you very much.
Any other questions? Going once, going twice. Sold. Herman, thank you very much for the presentation. Even as a non-coal person, I thoroughly enjoyed it. Once again, thanks to GeoExplore Store, who are our sponsors for this month's presentations. The recording of this will be put on YouTube at some stage, where you can all listen to it and download it if you wish. Thanks, everybody, and see you again, same time, same place tomorrow. I shall now close the meeting.
Thank you, Tanya.